This is a very satisfying part of our course. It's satisfying because it's addressing an issue that is on the forefront of most people's minds who live in coastal California. And that's the issue of fire in forests and its role in influencing their structure and how we can adjust management to address that. So our goals here are to talk about and learn about fire adaptation in forests, again tying back into basic evolutionary processes that we've been talking about so far in the class, discussing ways that fire and fire adaptations differ between California and other ecosystems briefly, and then going into how fire dynamics are changing in the West. Again, probably one of the reasons why this has been on your mind so much, and then going through some examples of environmentally driven wildfire disasters and what we can learn from them. Specifically, what we can do in terms of forest management ahead of fires, understanding that we're living in fire-prone ecosystems, what we can do now in order to address or minimize future impacts. So, fire is part of the landscape in California. The environment is fire-prone, and our vegetation reflects that fact. The species that occur in California forests are adapted to fire. Individual adaptation of species is really what I'm pointing to here. Plants must persist through fire in fire-prone habitats. Otherwise, they'll be driven to extinction. One of the most important ways that particularly our broadleaf species, persist through fire is through resprouting. Almost all of our major overstory species in coastal California resprout. Most of virtually all of the broadleaf species do this, and even one of our most important conifers resprouts, and that one in this case is redwood. Resprouting in conifers is uncommon, but redwood can do it. The other common overstory species, and really the only one of significance that does not resprout that I can think of is Douglas fir, but that species also has some adaptations to survival in fire, notably thick bark and larger trees. Here's an example of how rapidly forests in the Coast Range are able to reestablish firing following fire. This is a photograph from 2016 Soberani's fire in Big Sur. This was a major wildfire. It burned very hot, killed most of the overstory in many forests, and yet it killed few individual trees. And I'm speaking about genetic individuals of trees. Even with all of the above ground biomass killed in much of this photograph, the individuals are still alive and they are resprouting prolifically and reestablishing within this forest. This kind of resprouting reestablishment occurs in two ways. It can occur basally from the base of the tree through basal sprouts, or it can occur epicormically. And this is a photograph of California black oak, where all of the foliage has been burnt off these trees, but the canopy is rapidly reestablishing as buried buds within the branches and boles of these trees are growing out and reestablishing the canopy. How cool is that? I mean, this looks like total destruction, but these trees are actually still alive. Many trees can do this. Redwood can do it as well. Redwood can lose what appears to be able to lose all of its standing foliage, but then resprout. Another mechanism by which trees particularly in Mediterranean climates, this does occur in California, but it's less common than some Mediterranean climates. One of the mechanisms by which species persist is through serotiny. Serotiny is an adaptation where trees will enclose seeds in a closed cone, oftentimes by gluing that cone together with resins. and only releasing seeds when that cone is heated through fire. In some species, direct sunlight is enough to open the cones. These so-called, what we call in pines, we call closed cone forests. Serotiny is an excellent way of retaining seeds through a fire. This is a kind of aerial seed bank, and one which is fire resilient. So this is an example of bishop pine in Point Reyes National Seashore. And what's happened here is this is an extremely dense stand. It's post-fire regeneration here. And the way that you get this kind of regeneration is in part through the large seed bank, which is held within the canopy of this forest. This is a good adaptation to intense fire. And sometimes the persistence of these forests is actually dependent on reoccurring intensive fire. Bishop pine is not the only example of this. The first one that comes to mind for me is lodgepole pine, one of the most important pine forest types in the northern Rockies and through much of the western U.S. But serotiny as an adaptation is common in many other Mediterranean forests, particularly in South Africa, even though it's not occurring in pines. Now, as I said, we want to look not just in California, but think about adaptation to fire in other parts of the world. Here's an example from the Gibson Desert. This is an example of fire avoidance. In this landscape, fire tends to shift the dominance from woody plants to herbaceous plants. Even though the fire occurs with some regularity here, it's variable enough in space that there is persistence and coexistence of both fire and herbaceous species. It's just that the pattern of fire is differing in time and space, and in that way allows woody vegetation to persist. This is just this is something that I can't point to an explicit example about in California, but it's one that does occur elsewhere in the world. Likewise, this is kind of revisiting a forest type that we don't get to go to. This is an example of Acadian forests. Those are the wet forests, subboreal forests in northern Maine. These forests, the individual species are not adapted to fire, but fire still occasionally will happen there. And when it does, most of the individuals are killed. This kind of fire dynamic happens in a number of conifer forests across the world. Another example are many of the conifer forests in the Pacific Northwest. And you need to look no further than 2020 to see an example of how catastrophic those kinds of fires can be, how destructive they can be. The environment, it broadly speaking, is not prone to fire very frequently. But when the conditions are set for fire, they can be quite calamitous. This is part of these systems, and living with it really requires us understanding that, recognizing that, and managing the forests in light of that. Okay, so this week's reading is a paper that's been around for a while from Westerling et al. And it's a really great paper because it shows empirically, with data, using inference, not taking my word for it, that fire intervals in the West are changing. They are getting longer, and we are seeing increases in so-called mega fires. These are very extensive, the most costly fires that we deal with, whether because they burn so many acres and they cost so much to combat, or they release so much smoke that it creates public health problems. Now, we can predict when we're going to have a bad fire season. That's one of the really great insights that comes out of this paper. In particular, the temperature, the degree to which a summer or a spring season is hot will forecast how damaging a fire season will be. These temperature factors influence the persistence of snowpack, and in particular, when you have an early melting of the snowpack, either because the snowpack is small or simply because it's hot in the spring and the summer, those characteristics, those environmental factors are associated with an intensified fire season. This makes biological sense. The forests are essentially more dry. The trees themselves are more likely to carry fire, and the conditions are simply hotter. And wildfire conditions at the time of the fire are influenced by the ambient temperature. All of those things come together when you have an early melt of the snowpack, and when the temperatures are hot, you're more likely to have these kinds of damaging fires. So climate change is not increasing fire frequency everywhere, but it is increasing the frequency of very large fires in forests. Again, don't take my word for it. You can look at the data, and this paper is chock full of it. And furthermore, this has a clear empirical and inferential basis to it. If we don't have the snowpack, we don't have the resiliency of our forests. We're more likely to have these kinds of massive wildfires. And one of the insights from this paper that I think really resonates with me is that many of the factors that we can control, many of the forest management factors that we can control, many times will not matter if the snowpack is thin and it melts early and it is hot in the summer. Conditions are set up for carrying fire, and potentially carrying fire to a degree that we can't really address. The other insight that's in this paper, which I want to just point out, is that we're really talking about a band of elevations that are the most productive, between 500 and 250 meters in elevation. Why is that? Well, below those elevations, we really don't have very dense vegetation, and above them we also do not have very dense vegetation. The high elevations, it's too cold. The low elevations, it is too dry or too warm. At the mid elevations, where we have the accumulations of fuels, those are the forests that are most likely to be impacted by these kinds of events, so these kinds of environmental conditions. When we look across the West, we can see that fire impacts should be expected to worsen overall, with regional forecasts of increasing drought, more frequent drought, longer drought, and particularly hotter drought. And hot droughts is a concept that we were introduced to by Connie Millar and Nate Stevenson in the reading from last week, and the forecast is we're going to have more kinds of these environmental events. They are likely to lead to thinner and earlier melting snowpacks, and in that way magnifying our wildfire problem. How do we address this? Well, the environmental conditions certainly are climate change related. So any policy solutions that address climate change would help the West. We will address the problem or the potential for forest management to play a role in this slightly later on. We'll come back to it, but this is our what we're dealing with right now. And I say I want to come back to that right now because I want to point out something that is different than drought and hot drought, and it's something different that particularly we have to deal with in California, and this is adiabatic winds. These are downslope winds that are driven by high pressure systems that occur at higher elevations and essentially drive warm, dry air downhill. Now, if you live in the Bay Area, you might know these as Diablo winds. If you live in or around Los Angeles, you might know these as Santa Ana winds. Sometimes they're referred to here as Santa Lucia winds. They're all the same event. They're all the same meteorological event. And they happen in many different places. They happen on the Antarctic ice sheet, actually, even in an environment that's extremely cold. High pressure at high elevations will flow downslope, and it will warm up and dry in that process. What happens in California is we have high pressure systems that accumulate over the deserts, and those air masses move downhill towards the coast, and they are hot and they are dry. And you know that if you've experienced any of those three weather events that I mentioned, Santa Ana, Santa Lucia, or Diablo winds. It's hot, it's dry. It's like the deserts of the heart of the West have come to the coast. And when that happens, of course, we all go running to the beach. These events are scary. And if you've lived through one, you probably don't need me to tell you that. Hot winds, they're dry, and those winds can move really fast. The event that I like to point out is the Sonoma wildfires of 2017. This was a adiabatic event, and it was really scary and extremely tragic. Massive number of acres burned, many structures lost, staggeringly high cost in terms of lives and property. This is an event that I've been trying to study with a plot network in Sonoma County, and plot networks are an important way that we are able to quantify the impacts of fire and assess their intensities and their ecological impacts. I want to point out, even though these adiabatic wind events may be familiar to you living in California, not all of our damaging wildfires, not all of our worst wildfires are adiabatic wind driven. The Basin Fire and Big Sur, Sobrani's fire, the massive lightning complex fires of 2020, these are not adiabatic or wind driven wildfires. In this example, Sobrani's and Basin fires, they're both summer fires, and they followed relatively hot and dry winters, or hot and dry springs and summers. Also staggering in terms of the scale at which they impact the landscape, and substantial loss of substantial costs involved in these. Yeah, just staggering. And I always show this slide. This is because this is another set of fires that I work in. But this summer in 2020, we have the Dolan fire, which is partially overlapping these footprints, and there's another fire for me to study, go out, try to understand how it grew to the level it did and what we can do about it. Okay, so one thing you might be thinking right now is, has fire, or probably has occurred to you at different times in the past, has fire always been this bad? Has it always been this destructive in California? And this figure, while somewhat challenging to read, gives us lots of insight into that question. Has fire been as destructive? Has it been as common? What's changed in California? So what this figure is, and let me walk you through it. And I realize that my image is covering up some of the figure here. This is a reconstruction of the timing of fires in redwood forests. And granted, that's one forest type for California, but bear with me here. I think it's relevant, broadly relevant. And each of these marks shows you a fire event. These are reconstructed using dendrochronological reconstruction, which is basically dating events using tree rings. And the points themselves are fire scars. So what you've got here is you can pinpoint a particular fire based on the fire scar and where it occurred in the tree ring record. It's really, really valuable thing to do. And what you're seeing here is these are a number of different sites. They're in different places. They're from on a gradient from west to east. And that's going from wetter redwood forests to drier redwood forests. And here's what you got. You can see that the records are incomplete, more and more incomplete going into the past, but they're still a pretty long record, sometimes more than 1,500 years. It's pretty cool. Okay, so what have you got? When you particularly look before around 1800, you see many frequent fires. Many fires are occurring in California redwood forests, but they're not well synchronized across these sites, meaning sometimes individual sites burn, sometimes the fire seems to carry throughout an individual site, but not always. Sometimes it's restricted within sites or it's restricted to only individual sites. Now around 1800, that pattern starts to change. And what we see is that fire becomes less frequent and it's more synchronized across sites. So what happened? Again, prior to about 1800, we've got more frequent fires and they are asynchronous across sites. Afterwards, we have fewer fires and they are more synchronous across sites. What happened? Well, our landscape was depopulated of the people who were managing forests at that time. Talking about California indigenous people who used fire as one of their primary tools for managing the landscape. Around 1800, we have we have the development of the mission system, which contributed to depopulation. And actually, this trend of fewer fires and more synchronized across the landscape becomes even more prominent when you look later on in the 19th century, after the gold rush, when indigenous people were actively pushed off the land through campaigns of ethnic genocide. The fires become more synchronous across the landscape, and they become somewhat less common. So why would they become less common? Well, the fire is no longer being used as a management tool for very local areas, and instead we're kind of getting fire probably associated with the occasional lightning strikes and with accidents that occurred as people were establishing mines and so forth within the landscape. So what we've got is fires becoming less frequent here, but it's starting to be, individual fires are more likely to carry across sites. Now, after about 1910, this is not an error. There are no fire scars here. And why is that? 1910, 1930, we have the advent of the U.S. Forest Service, which had enacted a policy of fire suppression. What has happened over the last 300 years in California is that we have gone to a system, a relatively small and decentralized management group of managers were effectively managing the entire state for fire. Broad, large mega fires were extremely uncommon, if they even occurred. We don't have great evidence that they occurred, and they probably did from time to time, but we don't have good evidence of that from the tree ring record. What we do have evidence of is frequent small fires. That changed progressively as our management regimes changed, and now we're looking at about 100 years of fire suppression. And I think that it's fair to say that we're paying some of the price for that. Let's look at some examples of some of these problems. Here is an example from Humboldt County. This is near Willow Creek. This is a former old-growth Douglas fir plantation. It was poorly managed, it was abandoned, and it came back extremely dense. So what we've got here is both the toxic combination of fire suppression and a lack of management. So we kind of had, Forest Service had best laid plans here. They had a good plan, but it was not carried through. This was supposed to be a plantation, a sustainable source of timber for this community, and it didn't work because the silvicultural investments were never made. The thinning, the extra planning, everything that needed to be done to reestablish old growth structure here. It's a failure. It just is. This kind of condition can be managed with an intervention. That's the good news. There absolutely is a place for the management of stands. If you're a forester, if you're interested in forestry, that's probably not news to you. And we get all kinds of benefits from this. We can increase timber production, and we can make these stands more fire resilient. But it's expensive. Doing it is pretty straightforward. You need to do something. You need to reduce stand density. In this example, this management experiment, we're removing the broadleaf species because the conifers have higher economic value. And here's just some more examples of that. It doesn't solve all of our problems. There's still a lot of fuels here, but it is a big step in the right direction. Okay, so there's some other problems that we're dealing with, and these are biological agents of mortality. This is the one that I work on, sudden oak death, causes substantial and dangerous accumulations of fuels that do interact with fire to intensify fire, make it more difficult to combat, and also increase tree mortality and other ecosystem impacts. Here's some examples, and especially with tree mortality, these events create both canopy fuels and ground fuels, and both are problematic. Canopy fuels tend to contribute to the intensity of fire when it occurs. That increases the danger to direct attack activities, and ground fuels can lead to increased release of pollutants and impacts the ecosystem during the fire. They're both problematic. And don't misunderstand that don't just happen from sudden oak death. The bark beetle outbreak in the Sierra Nevada is another significant source of these kinds of problems, as are other invasive species. And here's an example of that. This is an abandoned vineyard in San Mateo County. This is it's a Genista, what do you call it? Scotch broom. This plant burns very hot. It has a long-lived seed bank in the soil. It outcompetes many native plants and creates this kind of positive feedback on fire dynamics. It is seriously quite a serious problem in terms of fire management. And that resprouting also gets us sometimes. You know, the resprouting of individual plants, of our plants' adaptation to fire is great for persistence of individuals and persistence of the forest, but it also leads to reestablishment of canopy fuels, and that can contribute to densification. Again, we can manage that. We can control forest density. We can't make it rain, but we can influence forest density. So there are aspects of the forest, of the fire problem that are in our control, and aspects that are harder for us to control. You may not say that they're totally out of our control. One, we should have a discussion about whether policy can address the issue of snowpack density and snowpack melting. Okay, many of these kinds of fire issues are also happening in the Sierra Nevada, even though these trees do not resprout. So the Sierra Nevada has seen the same kind of fire suppression that the Coast Range has, that redwood forests have, and the increase in density of these forests is contributing to our wildfire problem, no doubt. Now, you know, addressing the fire suppression, it's going to take a lot of work for us to get out of it, but there are some really promising experiments, especially in ponderosa pine. This is looking at Arizona, where I'm from. Just by doing some modest thinning and reintroducing fire, one can do a lot to improve the fire resiliency of our forests. So there are things within our control that we can do to make the situation better. Post-fire salvage harvesting is another good idea. It can set the stage for regeneration. We should not abandon management in stands that have been burned. Um, it would be wrong to just look at something at a big fire and then just sort of like wipe our hands and say, okay, well, that's taken care of now. That would be a huge mistake, especially for the communities that depend on these kinds of timber resources for their economic livelihood. And as I mentioned, we can manage these in a way that sets the stage for fire resilient forests in the future and sustainable timber. But it's expensive. No one should misunderstand. Solutions to these problems are not easy. That's why we haven't come up with them yet. And oftentimes, the solutions to these problems are going to involve a fair amount of expense and a combination of multiple approaches and approaches that are flexible over time.